Phase plane portraits are a good way to visualize the solutions and especially the stability of 2D state space equations. And so by state space, I mean that I'm considering a vector-valued differential equation that looks like this. And so if I'm just considering the 2 by 2 case where the matrix A is 2 by 2 and we only have two states to consider, then I can write that generally like this. If I multiply this vector by this matrix, I can get back to kind of where we started, expressing x1 dot in terms of this linear combination and x2 dot in terms of this linear combination. And this just emphasizes that in the end, what we're getting is by plugging in different values of x1 and x2, we can actually compute what the value of x1 dot and x2 dot are. And so we call this a vector field because it's essentially a field of vectors at different locations of x1 and x2. We get vectors that point in different directions because this derivative is a direction or a vector. And so what that means visually is that we can pick a point on this particular phase plane. So along the horizontal, we're moving in x1, and along the vertical, we're moving in x2. And if these are my differential equations that represent my state space system, that means I can evaluate the derivative x1 dot and the derivative x2 dot at any point if I choose a value for x1 and x2. So if I pick the value here, which is x1 is equal to 2, and here x2 is equal to 1, and I plug those values into this expression, that gives me the fact that my x1 dot should be 0, because I plug in 2 for x1 and 1 for x2, and those cancel, and that leaves me 0. And x2 dot is just x1, and so that is 2. And so the derivative x dot in that case is simply just 0, 2. And so I can visually describe that by an arrow or a vector that's pointing in the 0, 2 direction. And so it's conventional to, you'll see that all of the arrows in this plot are all the same length. And so you can either draw it this way or you can actually draw it with the magnitude so that it has length 2. So I'm not necessarily drawing it to scale, but this is the direction. And so this expresses the fact that there's 0 component in the x1 direction and 2 in the x2 direction. And so if you do that at every single point in this vector field, if you computed the derivative here, it would be pointing along that arrow. If you did that here, it would be pointing along this arrow. And so using a computer, you can easily generate these plots, and there are even online plotters, and they plot out this field of vectors, which describes what the derivative is doing at any given point in the phase space, in the x1, x2 space. And what's interesting and a cool feature is that if you select an initial condition, you can actually follow these essentially as tangent lines, because each of these arrows represents the tangent line. And the solution follows the path or the flow of this vector field. And so you see if we start at this location, the path that follows tangentially to these arrows goes something like this. And so the phase plane plotters that you can find online and referenced in the lab are able to do this. So if you just plot a point, you just plunk down a point, click here, it will solve forward and follow these curved lines and give you the solution. So this is a great way to visualize the behavior of the system in terms of the state space variables, as well as the stability, which is a primary concern for us.